Good afternoon, good morning, everyone. If you do happen to have your homework, I have one of them here. You can certainly give it to me, and I'll give it to Pat on my way back. If you haven't finished it quite yet, that's okay. It's not until 2 or 4 o'clock this afternoon, so you can turn it in to Pat by then. You're certainly welcome to use your lunch hour or whatever to get a few more problems correct, if you like, on the homework. Problem set number 2, which of course will be due next Thursday, is going to be the following problems in the back of Chapter 1. There are 8 of them here. 7, 9, 10, 13, 16, 17, 21, and 28. And, of course, the feedback question. Somebody just asked me, should you put your name on the feedback page? You don't need to put your name on the feedback page, of course, because it's anonymous feedback, but you need to attach it to your homework. So what happens is my secretary takes it, looks for the feedback page, she rips it off quick, and then checks off that you did the feedback on the master homework list, so you get credit for doing it, and then she just gives me all those torn pages basically afterwards so that I can kind of summarize feedback, which I'll do for the first time in next Tuesday's lecture because I'll be getting my first feedback today. Okay, so this is problem set number 2. I will remind you that it's a little bit in advance, but just in terms of your planning going forward. On the lecture for the February 1st, which is a Tuesday, will be taped ahead the week before, the Thursday before that. So that's basically a couple of weeks from today. But if you want to come to the live lecture, I think we have the time, but unfortunately I don't have it on my list here. I'll say next class, but sometimes people like to come to the live lecture, so I tell you when the tape ahead times for that. So it'll be on Thursday the 27th in any case. We have pretty much office hours stabilized. They're on the website, and in fact, I think everything is up to date. I know there are still some students having trouble registering. I've heard about more problems just yesterday. I don't know if anybody has any other problems other than registration. If you are having a registration problem, send a note to Pat and copy me. Pat Ashura, the course assistant. She seems to be successfully getting everybody into the class that wants to be in. Any other issues that may have come up? Okay. Well, what I would like to do then is today is to just review a little bit and pick up the nearest neighbor union bound, which we didn't quite get to in Tuesday's lecture. That's near the end of section 1.3 and 1.4, which is where we are right now. And so let me do that. We talked a lot about the additive white Gaussian noise channel last time, and it turns out using the concept of irrelevance, we found that all of the noise that we lose in replacing the real additive white Gaussian noise channel, which of course is an analog channel like any channel, by this vector channel where the noise components are basically the outputs of the match filters. When we sample them, if you were to insert the noise on the input to those filters, sample it, that would be the components of the noise here. Of course, if you have signal, those two are added together. And if that noise is additive and white, then we don't lose anything this way. It's good enough to just look at this vector Y. It only has n components in it. So we're kind of into already digital signal processing at this point. Okay, we've got a vector quantity, and any optimum decision rule applied to that vector quantity is as good as if we had applied it to the continuous waveform itself. And in fact, just some notation here. You'll see me often using the quantity signal to noise ratio. And basically what that is the energy per dimension on the input divided by the power spectral density of this noise. So this noise has a power spectral density n naught over 2. That's a two-sided density. Sometimes you write that as sigma squared also. These two things are equal. So that goes in the denominator. This is actually the variance of each component of this noise. They're all equal and they're independent. They all have variance sigma squared. That goes in the denominator. And then we take the total energy for the signal constellation. If it's more than one dimension, we need to divide by the number of dimensions, and that's EX bar. We're going to call that, obviously, signal, which is in the numerator to noise ratio. And often this is a convenient quantity to use to characterize the additive white Gaussian noise channel. Now the detector for such a channel, you can write EX bar here if you like. The detector takes the signal Y, and for this nice additive white Gaussian noise channel, we got a really simple rule for the ML detector, which is to pick the closest XI. If we do that, that's our X hat, and of course that can be converted back into the message. Mathematically, this is minimize over all the choices for XI, the difference between those XI values and the received vector Y, whichever one is closest, that's the decision. Okay, so that's kind of a nice rule that fits pretty closely with our intuition. We probably would have done that if we hadn't even bothered to take EE 379A. Most of you would have come up with a rule that probably was something like that to make decisions. So that's comforting. The additive white Gaussian noise channel follows intuition pretty nicely. The probability of error for that optimum detector, okay, is characterized by some quantities. And in fact, we bounded it in Tuesday's lecture. And to bound it, we needed to define an important quantity in communications called the minimum distance. And just as its name implies, it's the minimum over all signal points in the constellation that aren't equal of xi minus xj, that norm. Without the square, if we wanted to write a square here, then we put a square over there. Okay. So find the closest 2 points in the constellation. And that's kind of a weak link. And that's an important weak link in being able to evaluate the probability of error. And what we played with a little bit kind of near the end of last lecture was this probability that I gets confused as J. That contributes some of our error. Message I was transmitted, message J was decided, then that has a probability that we saw was Q of, and we could write it Dij, the distance between point I and point J, and of course that's always going to be less than or equal to Q of d min over 2 sigma, where Q is this function defined in the appendix. Now what I'd like to do, just briefly here, is I'm going to throw the plot from the appendix of chapter A on Q function probability of error here. It's going to take me a second to get my finger on the right page, so bear with me a second. And actually, I think it comes after the homework. Yeah, that's what. A little trouble finding it. Here, appendix. Oh, no wonder. I'm looking in chapter 3. No wonder I couldn't find it. Okay. Chapter 1 has these nice plots, which are easy to find if you're in the right chapter. At the end of the book, I'm looking at page 98 in the notes. And the lower figure in particular here, which is on screen, if you were to look at this Q function value as we plot here on the horizontal axis, you notice I have 20 log of d min over 2 sigma. That's the argument of the Q function, okay, that we were just looking at. And what happens is this is a logarithmic scale also here on the vertical axis, and it happens to be the probability that corresponds to this Q function value. And what you can see is even for very small increases, okay, this is 20 log of the argument. 1 dB is not very much. It's basically like about a 5 to 7% increase here in the argument. This falls off a factor of 10 around a range where we might feel comfortable. We're getting 1 error in a million, 1 error in 10 million, 1 error in 100 million. That's a pretty small probability of error in a transmission system. So any of those other terms that would be in a probability of error expression, which have larger distances, are going to contribute a very, very small amount to the overall probability of error anyway. The ones that really matter are going to be those weak links where we have the minimum distance, because they're going to give us the largest arguments to Q functions and those terms are going to dominate in the sum anyway. Okay, so it's all right to certainly replace every distance, as we did here, by d min over 2 sigma. That's kind of a nice bound, and in fact, if we have a larger distance, it's going to be really a lot less than this d min. But that's okay, it's an upper bound. What we found then in proceeding with the union bound, we said, well, let's just look over all of the possible signals and say, okay, the ways that we can make an error is signal 1 was transmitted and any of the other were decided, and then signal 2 could have been transmitted and any of the others could have been decided. And averaging that, what we found was that the probability of symbol error had to always be less than or equal to the number of messages minus 1 times q of d min over 2 sigma. Okay? And this is called the union bound. Certainly it works. The probability of error will always be less than m minus 1 q of d min over 2 sigma. Now we may have some terms in there where the distances were a lot larger than d min. So the m minus 1 may be a little high. Okay, we're counting everybody as a worst case distance, and not everyone necessarily was. So this is an upper bound. It may not necessarily be very close to the actual probability of error. It's kind of over counting possibilities or ways of making errors. So what we were about to get to at the end of last lecture is what I call the nearest neighbor union bound. And this is very heavily used in digital communications. And what's going to happen is we're going to define a quantity. Actually, a couple of quantities. First one is n sub I. It's going to be defined as the number of points, or signal constellation points, j not equal to I, that have a common decision boundary. Okay, so that's anybody who, if I start plotting decision regions, okay, which for the maximum likelihood detector, we know what that is. It's all the points that are closer, okay, to all the received values that are closer to that point I than they are to any other point in the constellation. So we start drawing lines. We have these boxes or squares or circles or whatever shapes they happen to be. And we go out and we touch one of those lines, okay, and the point that's on the other side of that line is the nearest neighbor. Now there may be a few of these, okay, as we look out in all directions from any given point, there may be a few nearest neighbors. So for any given message, it has n sub I called nearest neighbors. Those are the ones that have a common decision boundary. Anything that's way out on the other side of another point is being double counted in this union bound. We really don't need to include that because we already got it covered. The noise is big enough to make an error with the nearest neighbor, okay, then we don't need to count it again with a neighbor who's even farther than that away, because it's already been included in counting the nearest neighbor point. And what n sub E is the average number of nearest neighbors. So we take the expected value by weighting, so you could actually write this out, it's summation n sub I pxi. That's what this average means, from I equal 0 up to m minus 1. We could certainly do that. And find the average number of nearest neighbors. Then with the nearest neighbor union bound, it's not going to surprise you too much, the form is that the probability of error, it turns out, is always less than or equal to n sub E times q of d min over 2 sigma. Because we're just going to take the average over all the points in the constellation of these nearest neighbor counts. And so we're not double counting the points that are very far away. This will be tighter. Now it still may overweight some points because they may have a larger distance than d min. But at least we're not double counting points that are way far away in the bound. And so there's a proof of this in the notes. I don't think we necessarily need to go through that proof. You can read it. It's a pretty easy one to follow. What I'd like to do is instead look at a couple of examples of what this means. This bound tends to be a lot better for points that have larger M. Okay, have a lot of points in the constellation. The union bound is not as tight. A really nice example to illustrate this is a two-dimensional constellation. This is sometimes called 8PSK. We'll see it a little later as we proceed through the class being used. And it has 8 points equally spaced in angle around a circle. Okay. Obviously, the average energy is the squared radius of this circle if they're all, even if they're all not equally likely, whether they are, no matter what the probability distribution, they all have the same energy for it. Now, it may not necessarily be the best constellation design. Some of you are going to say, oh, geez, if I got 8 points, I got that much energy. If I move some of them inside, I can get a bigger distance. You're right. Okay. There may be practical reasons for putting points on a circle, even if you don't get the best distance. Now, there's a couple of things that we would look at in applying the union bound. The first would be, what is this distance between the closest 2 points? And obviously, those 2 points qualify as the closest two. And if we were to work out using basic geometry, you would get that d min is equal to 2 times the square root of the energy of the points, which is the same, times sine of 2 pi over 16. Okay, that's fine. In fact, if you were to work this in general, instead of having a 16 here, you'd have 2 times the number of points in the constellation. Okay, and you can just draw a triangle in there and use your geometry, you'll get that d min. Okay, so we know one of the things we need to know. The second thing is the number of points in the constellation. Clearly that's 8. So we have almost immediately, with a little bit of geometry, that the probability of error always has to be less than 7 times q of d min over 2 sigma. We got a 2 in the d min expression, so what we're going to be left with is square root of Ex sine 2 pi 16 over sigma. Okay, fine. We have that and can be evaluated. Now, as you look at that, you say, fine, but a lot of these points are really far away, and I'm kind of double counting in a lot of cases anyway. So what I really would want to do is look at this decision region for any point. Let's say we take this point right here. Okay, we got a couple of nearest neighbors, no more than that. And clearly, if the noise is big enough to throw me over that radial line to decide this, or big enough to throw over here, it could be any one of these points. But as long as that noise is big enough, I've covered all the possibilities for making an error. There's no other way to do it. If this component here is bigger than that, they're not orthogonal components necessarily. Okay. But a much tighter bound would be the nearest neighbor union bound, which is the same expression inside the Q function, but with a 2 out front. So we've improved by a factor of 3.5 our probability of error expression by using the nearest neighbor union bound. Okay, so that works for 8 points. Obviously, the more points we have in the constellation, if we had like 16 points around the circle, we'd still only have 2 nearest neighbors. So we're getting better and better on this approximation as the number of points increases. Yes, sir?
So on the graph that you showed earlier, you showed how easy it is by changing the get factors and and here we improved by a factor of 3.5. That's the point of these bounds.
Well, in this case, well, in this particular example, you're right. The point is actually the coefficient in front of the Q function because I didn't change the argument of the d min. But if I were actually to look at all the other points in this constellation, what happens is that the 2 closest points do happen to be at minimum distance here. So this is actually a very tight bound. Now, it turns out that sometimes I can get a really large noise. It could be big enough to actually throw me over both the lines, and it's still getting double counted. So this is not completely the tightest bound. But all we've been able to do here is to improve this coefficient here. Now, if I happen to have, a constellation, which would be a little bit strange in terms of its design, but let's suppose it had 2 nearest neighbors like this, and then we had another point way over here, and so our boundaries are going to look something like that, then this point, because the distance is so much larger, would contribute a term that would be much less than what these two contribute. So we could even do better by not necessarily including that point. In fact, what we might do in this case, for this point here, we would have n sub I is approximately equal to 2. We wouldn't even count this point. And in fact, as we go on in the 379B class, which I think a few people took out as sequence last fall, I actually take this average number of nearest neighbors and I only count points that are minimum distance, because it turns out it's really hard to find all the nearest neighbors when we get really complicated codes. So we simplify and just look for those that are at minimum distance. But for EE379A, all the constellations you'll see will be next to trivial to be able to work out how many nearest neighbors you have, and it's still, strictly speaking, an upper bound in that case. If I throw away this point and only count it as 2, it's not really an upper bound, but it's a very good approximation to the probability of error.